And we do have a code of conduct. Hello. We do have feedback. Okay. I don't know what that was. We did have feedback. Okay. Whoa, what is feeding back? We're feeding back very heavily. Okay.
It's one.
This is probably why. Let's just mute this. Okay. There we go. That's better. Yes. No feedback? No feedback. Yes! We solved a technical problem. Yay! I forgot what I was talking about. Yeah, so welcome to this Eastside AI ML IoT Meetup. It's kind of our second post-pandemic event, so thank you very much for coming. We're hoping to keep this Meetup series going, kind of keep growing and growing and growing over time. We currently have a free slot for next month. We try and meet up on the last Wednesday of every month. So we have a free slot for next month if anyone is interested in talking. August, I believe we have lined up. Loxley's agreed very kindly to give us a session for August. We might have a fun one for September, maybe get some hands-on with an AI IoT device. So there are a few devices that I'm going to be borrowing, so we might have a hands-on event in September. So we're looking to grow this community. We want anybody who's obviously local in the area, please come down and join us in person. If you're remote, great to have you with us, glad to have you online. Please, this is a live stream. Feel free to ask questions in the chat, and we will try and get questions answered in the room. Obviously, if you're in the room already, please ask questions. We do have microphones, so if you've got a question, we'll give you a mic to ask the question so the people at home actually hear what you're asking. Now, I do have to start with our code of conduct. We are on the Microsoft Reactor in Redmond, and we have to abide by the Microsoft Reactor code of conduct. This is for people in the room and joining online. And basically, be kind. Ask questions, talk to people, be friendly, but make sure that your conduct is not unbecoming. So be kind to everybody. Full details there. But yes, we have a zero tolerance policy. So if you breach our code of conduct, you will be removed. This is for the safety of everybody in the room. And so with that, I guess I will hand over to tonight's speaker, Mario. Come say hello, introduce yourself. Big hand, Mario.
Hello, can you hear me? Yeah. Right. Well, I'm Mario Palma, Mariojose Palma. I'm gonna be presenting here. I'm gonna be talking about deep learning and the reinforcement learning using C# and TorchSharp. So in my experience, I've been working on deep learning for around 4 years. Something about what I like about deep learning is one second. So something I like about deep learning is you can create any kind of program to learn based on experience, and this experience that we're going to be using for the program, it's going to be used in the future, and this program is going to become smarter and smarter over time. So on reinforcement learning, we have, I feel like it's like our life experience where you have a mistake or an environment, and depending on the actions you do in that environment, you get a reward or not. So if you are doing, great things while you are experiencing life, and you get positive rewards, and you say, okay, I'm gonna keep doing that. But if something, is wrong in that moment or didn't work out as you was expecting, then you get a negative point. So that's something I like about deep reinforcement learning. I feel it's like my philosophy of life, and we try to get as much positive reward over time. So the agenda for today is why we want to use deep reinforcement learning using C# and TorchSharp and not PyTorch or another language. I'm going to talk about what is TorchSharp, what is deep reinforcement learning, what is OpenAI Gym, and I'm going to show you a little bit of the demo I have for you on C# and how we are applying deep reinforcement learning to solve the problem or to win the game. So why we're gonna use TorchSharp and C# instead of the current solution that exists right now, like Python and PyTorch. So one thing is the learning curve. So 4 years ago, when I started learning about deep reinforcement learning, I signed off in a course, and this course was using Python, and I was like, okay, how hard that could be. So at the beginning, I was struggling, trying to translate what I was learning in Python with all my knowledge I already have in C#. I'm also trying to understand and learn all these new libraries that we don't have in C#. For example, we have libraries like Pandas, Keras, NumPy, and other that in C# doesn't exist. So the learning curve is big when you are coming from C# or a .NET developer. So I've been programming for 15 years in .NET environment. So when I came to Python, I was like, okay, this is something different. Another thing is the experience. So as a .NET developer, you have Visual Studio, and you already are familiarized with the debugging tool, like how to set up your breakpoints, how to debug like line by line, and see the actual values on that moment instead of printing the values while the program is running. So that's how I was doing in Python. So I feel like in .NET we have a great debugging tool that if you are going out of that, or out of Visual Studio, you're gonna struggle a little bit. The environment setup. That was a huge change for me, because in Visual Studio you just have to choose which .NET framework you're gonna use, write your code, play, and that's it, and you can see the program run. But if you go to the Python environment, you have to, well, you have many environments. You can set up or create many environments you want. And these environments have their own packages with specific versions. So if you are trying to find help or any example of code or internet and GitHub, you have to be aware of which version of the packages that other persons are using, because sometimes all these examples are different versions, and when you are trying to like copy and paste in your own solution, it doesn't work that way, because maybe the method or any function, a specific function, doesn't exist in that version. So I think it's a very we have an advantage on .NET because we have just one .NET framework. It's very easy to set up the environment, and it's almost similar in any other developer environment. And the deployment experience. So I was creating a solution using Python and deep reinforcement learning. Everything works in my computer. Everything was great. Like having the result I was expecting. The problem was like, okay, now I have everything running in my computer. How can I deploy this in a server, the development server, production server? And I was expecting, based on my experience, something similar to .NET. Like in .NET, if you have any applications, the deployment process is very straightforward. While if you are in Python, there is many variables you have to consider before deploying and running your program in that environment. So that's my overall why we are using, or I'm going to present how to use TorchSharp and C# to create a deep reinforcement learning application or solution. So we have TorchSharp. What is? TorchSharp is a .NET library. Right now it's in the .NET Foundation. So .NET is taking TorchSharp and they are developing more on that. And it's a framework that is gonna allow us using C# to grab or to call all the functionalities or almost all the functionalities that already exist on the Python, on the PyTorch SDK. So this is not something that's replacing or we are developing in parallel to PyTorch. This is just a wrapper. We are just calling the actual PyTorch library, and we are just translating that from C# to Python. That's TorchSharp. So here is an example of how it looks TorchSharp in C#. So if we take a look how for example, the initialization of the line number 3, the initialization of the layers experience is kind similar like what we use in PyTorch. So we don't have like the new statement as we used to use in C#. And the reason is the TorchSharp team are trying to create this wrapper, but keeping the same experience that the PyTorch or the Python developers have. So somehow it's gonna be easier to be able to copy Python code using PyTorch and paste on C# and make some few changes on the code. So there are some exceptions where, for example, the setup signal for the language code, for example, in C# we use are equal, and PyTorch we use, or Python we use semicolon to set the values. So that is something you have to change. But the idea by design, they are trying to keep the same experience equal. In the second line, also you can see how a namespace is not using capital there, and that's not something common on C#. Okay, so we have TorchSharp, that is our library to create our neural network. Now we're gonna talk about OpenAI again, where is our library of SDK to create our environment. This environment is, imagine it's like a game. So you have different, let me show you here. For example, in this, you have different scenarios or environments or games where with different rules and different actions you can take. For example, these environments come from Atari games where, let's say you have a joystick and you can move up, down, right, left, or you have other actions like fire or run faster or accelerate or brake. So with all these rules that are defined on these environments, you can start creating your reinforcement learning application to try to solve the problem and get as much reward as possible. So Open AI Gym is available or is developed on Python. That was one of the challenges I had creating the content for this presentation. So when I talked to Jim about what I want to talk, I was like, how hard this could be. I already have the Python code where I'm solving the problem. So if I have to write this in C# and I don't have OpenGym or OpenAI Gym, maybe what I can do is take a picture of the actual screen running Open AI Gym game in my screen, taking the picture and then controlling the actions with the keyboard C# code. But then I found someone in GitHub who ported the OpenAI Gym to .NET. So that's what we're going to be using today. I'm going to show you the code, and I think it's a great idea. I'm also going to share the link to you'll be able to download and start playing with it. This was the Atari games. We have these other ones this one are my favorite. Is show you how to, for example, the humanoid and the humanoid stand up and game or environment is where you can get a state of the environment, like how that human is standing up or is walking, and then using reinforcement learning, you can start. It's like you plug a brain on that humanoid and he starts learning how to walk because he's getting more reward while he's walking. So these environments here are one of my favorite. It's a simulation of how we learn to walk or how other animals walk too. And we have this one, the classic one. Right now, today, we're gonna play the card pool. We have these other ones who are very simple, but at the same time, it's a good exercise to start getting into reinforcement learning and then move forward. Okay, so what is reinforcement learning? So reinforcement learning, how I said before, I feel it's the way that an agent or a person or let's say baby or anything try to get as much reward as possible based on the current environment. For example, if you're a chess player, you try to look on the board, and then based on the current position of all your chips on the board, you calculate, if I take this position, I'm gonna win the game in the future. So you always try to think ahead of the future to get the maximum rewards. And in other areas too, like when babies are trying to learn how to walk, if they just get one step, let's say it's one reward point, but if they get 10 steps in a row, then maybe the final reward is 100 points because they was able to grab a cookie. So for them, it's gonna say, oh, if I keep walking more and more and more, maybe I can achieve more things or more reward in the future. So how we achieve that? At the beginning of the reinforcement learning, we have something called Markov decision process. Here is where we define what is this methodology to solve this problem. We have some elements here. For example, we have the state space where the state is the environment are the important points around where we take as an input to know what actions we're gonna take in the future to get the maximum reward. For example, the state could be the current position of the chips on the chess game, or it could be how I'm standing right now, and if I want to move forward, what is my state? It's like there is a stable floor here, or maybe if not, I have to jump over or what. So that's what we represent as a state. The actions are which actions are available at that moment to solve the problem. So in the games I showed before, in the actions could be the joystick controls, like the arrows, like left, right, up, down, or maybe just left, right. For example, in the game we're gonna play today, we just have two actions. We have only left and right. We have a transition function where after, and that means is after you take one of the actions, you are generating or you are getting another state. So for every action you take, you generate the following state and then move on. So with the previous examples, if I walk, if I give a, take a step forward, now I have another new state and I can decide which action I'm gonna do next. If I'm gonna have to jump or I can take another step forward. And the reward function. I think the reward function is my favorite. Because, for example, in this game is very simple. I'm gonna show you something I did extra for that. But in the reward function, you can, let's say, play a little bit because the program or the AI is gonna be smarter than you, maybe, to make or to get more rewards. Why is that? For example, in the previous game, I'm gonna go back a little bit. So in the humanoid game, the idea is for every step the humanoid go or forward, you get a reward. So he starts running, so the idea is like, oh, if you run, you're gonna get more reward faster. That's true. But as a human, we know how we walk. We walk stand up and one step for one step forward and then another. But the AI doesn't know we have to be, like in this position. The AI or the reinforcement learning is going to try different postures to try to run as fast as possible. And maybe it's going to find a better way to run as fast as possible, but it's not what we are expecting. So sometimes the reward functions is not straightforward, like just because you are closer to the goal, you are gonna get more points. Sometimes the reward function is more like, yeah, that the distance is one part of the equation, but the posture too. And if you move your arms back and forth, maybe you're gonna get more points. So depending of how you want to shape the way that this AI is gonna behave on the environment, you can tweak the reward function instead of just giving 1 point and that's it. So that's the reward function, and I think, I don't know, it's one of my favorite things. So in reinforcement learning or Q-learning, we used to have a methodology like this one, the Q table, that was trying to solve the problem, but without using neural networks. So in this example, we have a car who needs to go to get the goal on the prize to the right top corner. So if we see the current state of the car is where we can see the number one. Then we take an action to the right, to move to the right, because in the table, the second column and the row is the greatest value. So with the value is 0.4, we take, or we decide, take the right action, and then taking the right action, we get 0 reward because we are not getting the price yet, and then we generate a new state. So with the new state, we are in the right side, on the top and on the bottom. And with this new state, we can now calculate what is the next action we're gonna take. So if in the next action, we are getting the goal, the reward, then we update the table. And we update the values of the table. So what we can see here in the animation is the value is changing from 0.4 to 0.95. So next time that same state present to the AI, he is gonna know what action is gonna take. So at the beginning, everything here doesn't have any value. So the reinforcement learning process is like start exploring different options, and based of this exploration, then start creating this Q table or learning experience to maximize the reward. So this is the algorithm for the Q learning. So if we see on the last equation is where we have the Q value. The Q value take as a parameter the state and the action we are taking, and that's gonna give us a number. So this number is gonna be part of, we're gonna use this number to evaluate which actions we're gonna take next. So we have the R is gonna be the reward plus the difference between the next action after the current one minus the current one. So with that difference, what we're gonna do is, okay, if I'm here, I'm not gonna get any reward at this current state. What about the next state after taking the right action? So in that way, we can look at the future and see, or make a plan and say, okay, if I take right now, in the second state, maybe I'm gonna get a reward. So you can try to explore ahead if you're gonna get the reward, if it's the right path or not. If you want to make it smarter, you can add more timelines. So here we only have one step ahead, but we can add multiple times ahead and make it the bot smarter. It's like if you play chess, a very good chess player, it's looking at different possibilities of game over time, like let's say 4 movements ahead, instead of a beginner that is just playing on the moment. Okay, so what is here? I'm going to show what is the difference between the Q table and the deep learning or deep Q learning version. How we saw in the previous example is we have the state, we take an action, and this state action have X value. And with this X value, we can take the decision of which action we want to take for the current state. But with deep Q learning, we are replacing this Q value for a neural network. So this neural network is going to take the state, and then we're going to get as a result all the Q values possible for every action. And then to take the action, we're going to take the one with our maximum probabilities. And with that maximum probability, let's say if the action with a maximum value is action number 2, we're going to take the action number 2, and that's the one we're going to execute. So why we're going to use a deep neural network instead of QTech? So there are some cases where in an environment, or let's say a game, we can have many states or infinite states. So that table is not going to end in some cases. So to solve that problem, somebody came up with the idea to use a neural network, because the neural network is one of our tools to calculate probabilities in a very accurate way, let's say. So instead of storing all the possible states and assigning one value for each state, what we are doing is teaching to this neural network based on the state, which values on the Q value or on the action we are expecting based on our experience. So let's say this is how the Q learning or reinforcement learning has been evolving over time. So here is all what we talk about, put it together. So on the right side, we have the observation and the action. So the observation is our states. So we observe the states on the or the environment. Based on the environment, our little guy there is gonna decide which action it's gonna take on the environment. Our environment is our treater. What is happening behind the scenes? So what is happening behind the scene of this agent is, on the bottom we have the neural network. So in the neural network, based on these experiences, we are teaching the network, or we are executing a learning process where we are sending the states, and based on the reward we are getting, we are optimizing and changing the weight of the neural network, and the neural network keep improving over time. Another thing I'm going to show you in the code is this database we have in the top, where are the experiences that this AI is having over time, or playing over time. So without these memories and retraining, I think it's not possible, or it's not too efficient to learn and have a smart agent. I like to see it like if, for example, as a human, your database or this experience collection, you'll have it there in your mind. You'll remember all the good things you've been doing and all the bad things, or the one who gave you negative reward, positive reward. So you can keep getting these experiences, and based on these experiences, you think and say, okay, this was a good experience. I'm going to try to come up with more actions like that. This one was a bad experience. I'm going to try. Maybe you don't know what is the right answer, but you know what is the wrong one. So you can take the other actions you can take. So with this database, it's a collection of experiences you're going to have there, and over time, you're going to try to remember it, relearn from that past experiences to improve your model. So now we go to the demo, the code demo. Any questions so far? Oh, cool. Okay. Let me show you here. Okay. Here we have the code before explaining, like kind of line by line this code. I'm gonna run it. I would like you to see the final result, and then we go back to the code so you can kind of know, okay, what we are getting there. So here's the game. This is the carpool. The AI is trying to learn how to keep the pore balance. Let's say in real time. There are only two actions, left and right. So we can only move the car here, left and right. Here in our console application, what I'm doing is writing the maximum points that the actual AI is getting at the moment. Right now, stop it because based on the experiences the AI got, is relearning. Is relearning all that experiences, and then it's gonna try again other 100 games and see if he can get greater rewards than before, and so on. And I think this computer is a little slow for that. That's another thing. So for AI training, to train models on AI, depending of how big is the model, you need a faster computer. If you don't have in your hands something powerful, you can do the same, but you can change the amount of neurons or layers your model is going to have, so you can test faster. But while you have more layers, neurons in your model is going to be smarter, and maybe you're going to get better results from that.
Can I ask a quick question? In terms of performance, how much of an impact does the C# wrapper have on performance?
Oh, okay, that's a good idea. That's a good question. So something that I've been seeing on .NET recently, for example, we are using .NET 6, is they are focusing a lot on performance. So based on a website that they compare the performance between different languages, .NET 6 is faster than Python. So I believe in I don't know if in the AI area, .NET using TorchSharp is faster. I don't think so because it's a wrapper at the end. We are executing Python code behind or C++ code on behind. But using .NET 6 with the latest version, I know it's a lot faster.
Okay, so essentially there's no real performance hit as someone using TorchSharp versus using PyTorch.
No. Okay, this is something I would like to clarify. I'm using TorchSharp and C# right now because it's easier for me in the productive side to have something working. But it's not something I'm recommending for production use.
Right. So as you're building your models, this gets you going much quicker. But once you get your model finally built, then you just deploy that and use PyTorch rather.
Yeah, and also it's like the learning curve about the language. So if you're a developer who is not used to use Python as your code environment, maybe it's gonna be faster implementing something C# than going for the Python version. But if you are working something very production and critical, maybe you have to look out for a Python expert, our PyTorch expert, and start, working in that side while you are creating your, let's say, application, .NET APIs, or other stuff in .NET.
Yeah, thank you.
Okay, so here's again, now he got 21 points in the next try, and after 100 games again, he's gonna relearn this process. So what we're doing here, let me show the code. So here, in this side here, in this line number 9, we are initializing the environment, the carpool environment. This carpool environment is coming from this gym.net library that I mentioned you about. I'm going to share the link at the end of the presentation. Somebody did a great job here because the OpenAI I mentioned is available only in Python. So that was for .NET. And initializing this environment here, I can get the current state for the beginning of the game. So that's what the line 12 is. If we jump a little bit to the line 29, is where we are taking the state and we are passing this state to the agent to act based on that current state. And when you say, okay, who is this agent for? So the agent is the player or the person, let's say, and is the one here I'm creating or initializing. So I have now the agent, I have the state, and in the line 29, I have the action based on that current state. So remember the action here can be left or right. And where I have this action, created here for the agent decide which action is taking, we are calling this environment step. When we call step in the OpenAI Gym library, is this step you moving forward or any action you are taking in the current environment to get the next step. So the step takes as a parameter the action. We are passing the action here based on the decision of this agent. And as a return, we are getting a next state, how much we get from the reward, and if the environment is done or not. When it's done, means in this game means we lose because the pool went out or inclined like 25. I don't know if it's percent or degrees, but 25. But leave it there. So that means we lose the game. Done is when you achieve your goal, and it's when you make 200 points. So the AI is smart enough to keep the balance of the pool for 200 steps. Let's call it seconds if you are not familiarized with this environment. Okay, so this reward here is the one is just 1 to 0. So if you lose 0, if you keep it in this angle up, you get a 1 reward. So this is something I want to show you. Is this custom reward I come up with. What I'm doing here in this custom reward, that formula, is I didn't want just to get 1 reward point, just to keep it straight or a little bit, strange. I wanted to be more precise to make our AI learn faster and more accurate. So that formula in the line 31 is calculating a value from 1 to 0 based on the angle of this pole. So if the angle of the pole is 25 degrees, let's say the degrees, 25 degrees to the right or to the left, it's 0 points, but if it's right in the middle, it's in one entire point. Anything between is any value which is could be 0.5, 0.75, and like that. So that way, I feel it's more precise, and also the AI gonna feel more motivated to keep it in, like real straight. That the value there is 0 degrees, so to try to keep it in 0 degrees. So after taking this step and getting the next state, the agent, we call the agent to take the step to say, hey, we took the action you decided before. Now I'm gonna pass to you which state and action we already take. I'm passing that custom reward that we create, and also the next state that is generated by the environment based on the action we took. Here done, and the game come. We're gonna go over that in a little bit. So now here I'm gonna go inside of the agent state. Agent step. So here we have our memory. So remember in the presentation we have this database on the top. So what I'm doing here is taking all the experience. Here is taking all the experience, like which action I took, what next state was generated, which state was the current one, and how much reward I got. So with this memory, I'm gonna be able later to take a batch of experiences and learn from that. So after storing that memory in the computer, here what I'm doing is how many times I want to learn. You can learn every game. Like you play a game, you start learning. But this if statements here is saying, okay, you're gonna learn every 100 games, and I have this variable right here. So every 100 games, I'm gonna go inside here. I'm gonna get a sample of these experiences. So in the experiences, I have around 10,000 experiences I'm storing, but from these 10,000, I'm just I think I'm getting 1,000 experiences. So you can get any how many experiences you want. So with all these experiences, and this sample is random, it's not like the last 100 games, you can keep the AI model learning based on what already experienced before. And then we have this learn method we are executing here, passing all these experiences. This is I think it's one of the most exciting parts. So for all these experiences, we create tensors. Tensor is a data type used on AI, and for C# wasn't very common, but now with TorchSharp, we are enable the developers to start using tensors data type to create AI models and machine learning and other great stuff. So I'm taking all these experiences from double arrays, transforming that to tensors, and that's what I'm doing from the line 57 to the 61. I'm taking all these arrays and using it here. So we have two neural networks here. We have one neural network called target and the other local. So the local is the one who's gonna learn and be optimized to change all the weights on the neurons. And after the locals learn all these experiences and all these neural change based on experience, we want to start updating the target weights to be used for the next states. So what we are doing with the target network is calculating what is going to be our Q value based on the next state. So we are going to have, we're going to be one step ahead to be able to take the decision for now. So here in the line 63, we are calculating or getting the Q value, the maximum Q value based on the next state tensor. Here is where we are using the next state. The formula I explained on the presentation before is this one, where we're gonna take the rewards, and this place here is where we are getting what is the next reward we're gonna get, and based on that reward we're gonna get, we can take the decision and say, okay, I have, well, in this case, two possible actions. With these two possible actions on the next day, I'm gonna get these rewards. So you can, there is some examples over internet to set up this formula to be more greedy or more, let's say, not too greedy, I think is the word. And you can set or the value of that next reward with a discount factor. So right now, I'm just discounting 1%, but you can say based on the time you are evaluating, let's say if we have 2 or 3 times ahead, we can start discounting the reward point because at the end, we think we're gonna win on the 4th step ahead, but we are not 100% sure. So the discount, the 4th step ahead is gonna be lower because the discount is gonna be greater than the actual reward we have in the next step. In the next step, we know kind of like for sure, and in this case it's like 9%, we're gonna get that reward. But in the second or the next step after that one, maybe it's gonna be an 80% and so on. So on this line here, we are evaluating the Q value, but now for the current state using the local network, not the target. So with these two values that we are calculating here, so the future reward plus the current one, we can execute this loss function, where is with this loss function we use that loss function to be optimized using the optimizer that we create or we initialize here when we are creating our neural network. So this optimizer here, right now we're using this Alan optimizer or algorithm. There is many, but in this case we are using Alan. So with this loss function, it's gonna be the one that here is expected and the target. We're gonna calculate what is the difference, and with this difference, we're gonna go backward on the neural network and start changing all the weights, so the AI model start learning how to do it better next time. And after our local network learn or change all the weights, then we start updating all the weights for the target network. So here for each parameter, when we call parameters here on AI models, is all these weights connected, or all these connections between the nodes in your neural network. So all these connections have weights. So what we are doing here is updating the weights based on what our Q network local learn. And the last thing is the method act, or how we choose the actual action. So in this line here, it's pretty simple. We get the action values calling the forward method from our local network. And here we are choosing which of the actions have the maximum value. For example, in this case, 2 actions, we have 0 or 1, and they have a value behind. So we can choose which index is the one with a maximum value. And in this line here is where we're exploring. And that's something I wanted to give for last. So in the act, we are passing this EPS value. So this EPS value is I initialize on 50. So the 50% of the time at the beginning of the game, the AI is going to start exploring options. So there is a chance here that 50% of the time is gonna take an action based on the result from the model, and the other 50% is gonna be a random selection. So over time during the game, we are at least counting 1% of that 50 initial value. So over time, the AI is going to start taking more, well, it's more probable, it's going to take the action more from the network than randomly. But it's very important to set something like that at the beginning, because you have to let out your AI model to explore different actions. So maybe it can find the right path. So for this example, that's all on the code. Well, we render the actual screen from the environment. Here it is. So I'm gonna run the program again. So we can see it for time. And now we have a better idea of what it's doing behind the scenes. So now we've got 27 points. So in average, in other projects I've seen on our internet, after 600 games, the AI can achieve the 200 points. But well, here it's going to take a little while to achieve that. That's all. Any questions? I hope everybody liked it.
Hello? Yay, it's working. Yes. Question over here.
Awesome, thank you so much. First of all, fantastic presentation. My question is specifically on, like, I know in like some AIs, there's like they give you like a confidence percentage. Like we have 95% confidence that it can solve it in like 600 plays or an X number of seconds. Is that a thing with like the programs that you were showing us?
Do you mean like if I'm confident 100% that maybe in 600 games we wanna solve the problem?
Yeah, similar to that, but like, yes, kind of like, yeah, what's like, if they give you like a confidence like percentage of like, hey, we know that we can figure this out. Like, I think the way that I'm thinking of it is it's like, okay, maybe it's like when a stakes moves back and forth, getting it to be like perfectly straight in 600 isn't high stakes, but I can see reinforcement learning being used in a way that it's like, okay, this is very high stakes. It needs to figure itself out really fast and be very precise. So it doesn't have like confidence like, oh yeah, I can, like, we know this AI can figure it out in like X number of plays or times or reinforcements.
Okay, I think I would like to say yes. But I've seen, let's say, lucky strikes where after 100 games, for example, yesterday when I was testing before coming here, I got 120 points after 100 games. So like in a game 120 something, I got this 100 points. I was like, oh, that's awesome. In the 2 rounds we did here right now, we got different points, and the reason is when you initialize a model in your computer, the weight of the neural network are always random. So they initialize with different values, and if the values are right, you're gonna get a better result at the beginning. But if not, the AI model has to be experienced more to try to figure out how to get as much reward. Also depend on the code. So, for example, I show my constant reward formula, and maybe using the other reward formula, like just 1 or 0, maybe I'm gonna get a faster result, or maybe not, or more slower. And depends also in how many neurons have your network. So that's why I want to say yes. I want to say average, let's say 600 episodes is how they call it. But all depends.
That is an awesome answer. Thank you so much.
Yeah, you're welcome.
Awesome. Any more questions? Okay, I have a question for you.
Okay.
So this meetup, this is AI, ML, and IoT.
Okay.
So how confident are you that you could train a model using that gym and then actually put that model in a trolley with a pole coming out and actually have it work?
Okay. That's a very good question. I'm gonna say I'm confident that the program works, but there is other variables that we have to take in account when we go to the real world. For example, I used to work with IoT on the boats environment. So we plug in some sensors there. We create some formulas and these formulas were like the reward function, where we were trying to save as much gas as possible based on the data of the sensor, like wind, the current flow, the RPMs of the boat, and the speed, and other stuff. So when we were creating this formula on our computer in a simulation, it was awesome, worked. But when we went to the real scenario, this formula needed to be adjusted based on things we can calculate. For example, we were using also the GPS signals for some calculation, but there is some drift on the GPS calculation. So, and the drift is because the Earth is moving right now. And we didn't count for that drift in our simulation, because in the simulation, you say, okay, this is the actual location, and the Earth is not moving. But when you are in the real world, the Earth is moving, and it's like, what is this error? So coming back to the pole, maybe our program is right, but the friction of the pole moving back and forth affects the formula or the reading of that moment. So if we are having a pole with this car moving around, very lubricated, in a, I don't know how to say, like, when you have an environment without an atmosphere and an emptiness, vacío, I don't know how to say in English, but when nothing is affecting, like if the car is moving but the wind of that room is not affecting the movement, yeah, it's gonna work.
Right. Okay. So as long as the friction between the pole moving kind of matches what's in the model, and the ability for the car to change direction matches what's in the model, and there's no wind. Yes, kind of the physicist idea of the perfect molecule in a box with no influence of the outside world, which obviously doesn't exist. So.
Exactly. Yeah. For example, let's say we come up with a card here for our next event, right? And for some reason we have a fan, like pointing the pole.
Or the aircon, the thing
Or
above
the
you.
yeah. So that's something we are not taking in account in our current simulation. So that may affect the result in real life.
So it kind of feels like we should come back in one day with your code and a car on a pole.
Yeah, I would love to
actually try and rerun the simulation, essentially, just so rather than having running as a simulation, actually get the car going back and forward and kind of train it on the real world and see how well it responds.
Yeah, I would love to do that.
That'd be fun. I think we should do that.
Yeah.
Awesome, cool. Any other questions? No? Okay, well, thank you very much to our speaker, Mario. Thank you very much for joining us. I'm just going to come on camera as well. Thank you very much. Thank you for everyone who attended. Thank you for the viewers online. We should be back last Wednesday of the month. So we'll be back here next month. Talk still to be decided. If anyone wants to volunteer, please do so. If not, we'll try and rope someone in. Worst case scenario, it won't be me because I'll be on vacation. So, but yeah, hopefully we're back here next month, last Wednesday. If not, last Wednesday in August, we should have a great session from last week here. So with that, thank you very much for joining. On the stream, thank you. We don't have pizza for you, I'm afraid, but we did for the people in the room, we do have pizza. So thank you very much and enjoy the rest of your day.
Thank you.